In this lesson, we'll go over how to find limits algebraically as opposed to numerically and graphically. But first, we want to talk about some limit laws. And we start with this assumption: given that the limit of f of x as x approaches c and g of x as x approaches c both exist, we're going to cover 5 of these limit laws. So the first one is this: the limit of any constant term as x approaches c is just the constant term, because there's really nothing else you can do to it. So the limit of k is k. The second one shows that the limit of a function multiplied by a constant term is the same as taking the limit of the function and then multiplying by the constant term. The next one shows that the limit of the sum or difference of two functions is the same as taking the limits first and then adding those two together. So the limit of a sum is equal to the sum of the limits. In the same way, we can talk about the limit of a product. The limit of a product is equal to the product of the limits. So the limit of f of x times g of x is the same as finding the limit of f of x and finding the limit of g of x and multiplying those answers together. And in the same way, the limit of a quotient is equal to the quotient of the limits, provided that the denominator is not equal to 0. So those are the limit laws. I'm going to show you how we could use the limit laws to evaluate some limits. So if you look at the first example here, I want to evaluate the limit as x approaches 2 of x cubed plus 4x squared minus 3. Well, what we can do is break this up into 3 tiny functions, and then use the laws to evaluate them. So I'm going to break these out, and when I separate them, here's what I get. I get the limit of x cubed as x approaches 2 plus 4 times the limit of x squared as x approaches 2 minus the limit of 3 as x approaches 2. And then we evaluate each one based on what we know about the function. So x cubed, that's the cubic function. So he crosses at the y through the origin. That's a terrible picture, so let me just forget that. He crosses through the origin, and when x is 2, we know it's continuous everywhere, so when x is 2, then 2 cubed is going to be 8. I know it has a value of 8 because I know the function's continuous. Same thing with x squared. That's a continuous function. So as x approaches 2, 2 squared is 4, but then you multiply it by the constant in front. That's the other limit law. Finally, the limit of a constant is just the constant itself. So if I were to evaluate this, it's 8 plus 16 minus 3. That overall limit is 21. Now, if you think about it, I get a 21 when I evaluate the limit. If I were to evaluate this, just find the value of the function, I would get the same thing. I would get 8 plus 16 minus 3. So evaluating this limit in this case is the same as just evaluating the function. Alright, so we'll do another example like that, and then we'll save the third example for class. So the limit of, as x approaches 3, of this guy, this is a product, and then this is a little difference inside the product. So I'm going to use the laws to break them apart. The limit of a product is equal to the product of the limits. So here we go. The limit of this product is the same as the limit of x squared as x approaches 3 times the limit of 2 minus x as x approaches 3. I could even break this out more, but I think we can leave it like that because this is a linear function and we can figure out what that is. This guy is continuous. This guy is continuous. So x squared, as x approaches 3, my value is going to be approaching 3 squared. So that part is 9. Here, when x approaches 3, the value is going to be approaching 2 minus 3, which is negative 1. So the overall limit is going to be negative 9. For those examples, all we're really doing is evaluating the function at a certain point. And as long as the function is continuous, everywhere the function is continuous, that's all we have to do. So that's always the first thing we look for, continuous. I think that's spelled right. That's what we have to look for first. If C is defined at that location, all you have to do is evaluate the function. So if f of x is a polynomial function and C is any real number, Because we know polynomial functions are everywhere continuous, then the limit as x approaches c of f of x is just f of c. You're just evaluating the function. And the same thing is true for a quotient. If f of x and g of x are polynomials and c is any real number, then the limit of that quotient as x approaches c of that rational function is also going to be the same as when you evaluate the function. As long as it's defined, that means g of c is not 0, f of c over g of c. As long as, if and only if, g of c is not equal to 0. So in a lot of cases, the limit of the function is the same as the value of the function. So let's look at this example. The limit as x approaches 2 of this rational function. Well, if you replace 2, if a rational function is going to be undefined, it's going to be where the denominator is 0. But if I put a positive 2 in here, my denominator is just fine. It turns into 4. So all I have to do to find this limit, I don't have to go through all the laws. I just have to evaluate this function at 2. So that means it's going to be 2 squared plus 5 times 2 plus 6 all over 2 plus 2. And when you get done, that's going to be 4 plus 10 plus 6 all over 4. That's 20 divided by 4, and you get 5. That's all you have to do. So the first step, always, is to check and see if where you're evaluating the limit, if that point is makes the function continuous there, or if it's undefined. And if it's continuous, just evaluate the function and save yourself a lot of work. So now let's look at this guy. The limit of the same function, but now I want to evaluate it at -2. Well, if I put a -2 in here, my fraction becomes undefined, and I can't just substitute it in and evaluate it. So if I have a rational function like this, if I want to evaluate the limit, what you can do is factor whatever you can and see if we can reduce this down. So we're going to rewrite it into some equivalent, into a function that's going to have an equivalent limit, but it's something where we can evaluate. So that's what we're going to do. We're going to factor and reduce if it's possible. So x squared plus 5x plus 6, that's going to factor into x plus 3 and x plus 2 because it's factors of 6 that add to 5, and then I'm over x plus 2. Well, these are going to reduce down to 1. And I'm left with an equivalent expression for the limit. As far as the limit goes, this function will yield the same answer. I'm now evaluating the limit of x plus 3 as x approaches -2. So now I can evaluate because he doesn't have any issues. All I have to do is substitute in -2 plus 3, and that limit is 1. Now there are 2 more situations, special cases that we're going to do to evaluate limits. This is the first one, factoring and reducing. The second one is simplifying a complex fraction, and the other one is rationalizing a denominator. And we're going to focus on those in class. So we're going to finish these notes together in class to make sure I have your attention and you're listening to me, and we can go over it together and you can ask questions along the way.